In this video, I'm going to introduce you to the Rational Zero Theorem. So let's get into it. First thing is the definition of the Rational Zero Theorem, which is that a polynomial has as many zeros, possible zeros, as this quotient can describe. So P over Q is just the letters that they use to define it. What it really represents, though, is that you're trying to figure out all of the factors of the constant. So whatever number, usually at the end of your polynomial, the constant's going to be the one without a variable attached to it. So figure out all the factors of that number and put them over all of the possible factors of your leading coefficient. The leading coefficient would be the one in the front, as long as it was in the correct order. The leading coefficient will always be the one with the highest degree or highest power. So really, let's try and break this down and figure out what the heck is going on. For example, if you had this polynomial, the constant would be this number in the back. It's the one without an x next to it. So you're trying to figure out factors of -6. Well, we know that 6 and 1 are possible factors. 1 would have to be negative to give us a -6. So -6 and 1, but we could also have 6 and -1. Those are also factors. So really we have positive and -6, and we also have positive and -1. We also have 3 and -2, but we could also do -3 or +2. So again, we have positive and -3, positive and -2, and I believe that's all of them. So there's our possible factors of our constant, and if below that, below each of these, we're putting our Q value, which are the factors of the leading coefficient. Well, the leading coefficient is this number in front here, which is implied that it's a 1. So we're looking for factors of 1. Well, 1 and 1 are factors of 1, but also -1 times -1, that also gives us a +1. So really we have positive and -1 as possible factors. So we put that below each of our possible factors of the constant. Since we have a ratio here, we want to simplify that ratio. So positive and -6 divided by positive and -1 would just give us a positive or -6. So we can take that 1 out of the denominator when we simplify. Really, we could do the same thing for all of them. So all of our possible zeros are listed there. We got 2, 4, 6, 8 possible zeros. Since we live in an age where we have graphing calculators, we could take a look at our graphing calculator, graph this function, and see which of these possible zeros are actual real zeros. And so let me bring up a graph here. So when we graph that function, hopefully you've done it, and we could sketch our graph knowing that the end behavior is going to be similar to a linear equation with a positive slope. So we're going to be going down on the left, and we're going to be going up on the right. And what happens in between is what we look at our calculator for. So we find that the zeros are at, what is it, -3 here. So we're going to cross there, and then it's going to cross back at -1, and then turn around at, looks like +2 is our other zero. So there is our graph, a little bit more accurate. Here's our 0. Here's our 0, and here's our 0. So out of those 8 possible zeros, we found that there's really only 3 real zeros, and they were at -3, -1, and +2. So we can use that knowledge here, and sometimes you'll see questions on a test or on an SAT or something where it says, even though you can use your calculator, you got to prove it algebraically. Well, I mean, we know what the zeros are because we looked at our calculator, but let's actually prove it algebraically by factoring, and we're going to use what's called synthetic division to help us factor here. Alright, let's rewrite that function. X cubed plus 2x squared minus 5x minus 6. We knew that, looking at our graphing calculator, that our zeros were -3, -1, and +2. So let's prove it algebraically. We're going to start using synthetic division to help us factor. When we do that, we place one of our zeros in our little box here. And if you don't know what synthetic division is, check out that video. I'm going to use +2 just because it seems easy. So I'm going to put my 0 in the box. I'm going to list my leading coefficients here. So I got +1, +2, -5, and -6. I'm going to drop the first term down. I'm going to multiply 2 times 1 and write that right there. And then I'm going to add my columns. So 2 times 2 is 4. Then start the process all over again. 2 times 4 is 8. Add my column here, I get 3. Multiply 2 times 3, get 6, and add it, and I should get a remainder of 0 if I am factoring correctly. Factors should not result in a remainder. So then I know that these are the leading coefficients of my answer. So I still have this as a factor, and if I write my 0 in a factor form, I need to think about the opposite. Because if 2 is a 0, then my factor form must be x minus 2 in order for a +2 to give me a 0 there. Then rewrite this. This is going to be an x squared. I always start with one less than my original polynomial. So I got x squared here, plus 4x to the first power plus 3. So here are my two factors. That's what resulted from using synthetic division to factor. And I know that this is going to be this 0, so hopefully I can get my -3 and my -1 zeros out of this by factoring. Let's see what happens. If I use a quadratic factoring pattern here, I can factor this quadratic. Factors of 3 that add up to 4, well, that must be +3 and +1. And then if I set this equal to 0, I can find my zeros. So we knew that 2 was a 0 from that set, -3 is a 0 from this set, and -1 is a 0 from this set. Does that match what I saw on my calculator? Yes, and I have proven it by factoring and showing everyone that algebraically I still get the same thing that I knew I got by looking at my calculator. So there I use synthetic division to factor and to find my real zeros, and I use my calculator to kind of double check all my work. Alright, let's do one more example, a little quicker this time. I'm going to show you something that you might see which makes it a little bit trickier. Let's say we have a function that looks like this. Notice that my function is skipping some degrees here. I'm skipping my x to the third and my x to the first power. Keep that in mind, because we're going to have to do something different when we synthetically divide. So if I list my possible zeros first, I want factors of my constant. That's going to be what? 4 and 1, -4 and -1, 2 and 2, and -2 and -2. So here we got positive and -4, positive and -2, and positive and negative or -1 there. Those are all my possible factors of my constant. And then I want to write that over my factors of my leading coefficient, which is a -1. Well, factors of -1 are -1 and 1, and 1 and -1. So really I just got plus or minus 1 are my only options there. If I simplify these ratios, I get my possible factors. Just positive and -4, positive and -2, and positive and -1. So we got 6 possible factors there. We look at our calculator, plug this into your calculator, and look at the graph, and you should be able to find your real zeros. So if we look at a graph here, found that we get real zeros. We're going to have, what do we got? A negative leading coefficient. So we're going to have a parabola that's opening down, but it's going to be an M shape because our leading degree is higher than 2, but still even. So I'm going to have some basic shape like that. And I know that my real zeros are going to end up at -2 and +2. And so I should have some sort of graph looking like this. Right? Okay. So knowing that information, let's use synthetic division and prove it algebraically. So I'm going to set this back up here. -x⁴ plus 3x² plus 4. I know that my zeros were, looking at my graph, there were 2 and -2. I'm going to use one of them and put them in the box. I'm going to use +2 because that's usually easier. List your coefficients, and remember that we're skipping some, so we got to use zeros in spots that we're skipping. So we got -1 for x⁴. I have a 0 for x⁵. I have a +3 for x². I have a 0 for x⁻², and then I have a +4 as my constant. Drop my leading term down and start my synthetic division. 2 times -1 is -2. Add your column, you get -2. Multiply. 2 times -2 is -4. Add your column, you get -1. Multiply again. 2 times -1 is -2. Add, we get -2, and then multiply, and we get our resulting remainder of 0. That's what we want. Make sure that we factored correctly. So if I list this as a long polynomial here, we got -1 x⁵. It's going to be one less than what we started with. Minus 2x² minus 1x minus 2. And we started, if I rewrite that as a factor, I have to say x minus 2 if 2 is going to be a 0 from that. So then we can factor. Let's see, what could we factor? Well, I know that I always want to factor a -1 out of any polynomial with a coefficient of -1. That makes it a lot easier. I'm going to rewrite this at the front. So we got that -1 out of it. That's going to give me positive, 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 and positive. And we'll rewrite that x minus 2 off there. I think we can do grouping here to factor this. So if I take out an x², that would leave behind an x plus 2. And if I take out something from here, I think I could take out, well, just a 1, right? And that would leave x plus 2 again. I'm going to rewrite this up at the top here, give myself some more room. So x minus 2, just right there, I'm going to write it at the front again, times, what do we got? There's a minus out in the front there. Not going to be much of a difference. We got x² plus 1, and then we got x plus 2. Can we fit it? There we go. Set that equal to 0. I can find my zeros and see if it matches with what we got from our graph. Right here our 0 is going to be positive 2. Here we're going to have a -1, and then if we square root that, we're square rooting a negative, so that's not going to be a real 0, that's going to be an imaginary 0. We don't even pay attention to that one. And then we got a -2 from that last one. So our real zeros do end up being only positive and -2. Exactly what we saw in our graph. And so yeah, a little trickier there. A lot of different methods you saw. Hopefully you can put it all together and factor polynomials using synthetic division to find real zeros.